Okay, Fred, should we start? All right, let's get started. Thank you everyone for attending this time of flight secondary ion mass spectrometry introduction seminar. This is the first time I'm using the online form to do this. It's a little bit weird, but I will try to make sure it goes smoothly. And you can stop me at any time since we don't have that many people here. You can stop me anytime to ask me questions. I will make sure this can be done within an hour. If not, then we can plan next time or maybe go to a little bit longer. All right, so today I would like to talk about time-of-flight secondary ion mass spectrometry. And this is one of the instruments in our surface analysis lab. We have this instrument for more than 10 years. It's still in a very good working conditions right now. So the outline of my talk today will include, I will first talk about what is secondary ion mass spectrometry and what is the difference between the dynamic SIMS and the static SIMS. We call it D-SIM and S-SIMS. And then I will go over the TOF SIMS instrumentation part. What is the source? What is the how the time-of-flight mass analyzer works? And then I give you a lot of applications of time-of-flight SIMS, which most are collected using our instrument. All right, so the first two parts. What is SIMS? Before I'm talking about what is SIMS, I would like to talk about in general the analytical instrumentation instrumentations. So most of the instrument we're talking about involves the source. Source can be ions, can be electrons, can be X-rays. For example, the SEM, the scanning electron microscopy using electron beam, SIMS using ion beam, X-ray diffractions using X-ray source. And then most of the thing like you bombard the materials using ions, electrons, X-rays, and you generate the ions or electrons or neutrons or X-rays, and you are using a detector to analyze those things. In SIMS, we are using the ions as the primary ion beam, primary source, and then we are analyzing the ions, the so-called secondary ions that are coming from the materials. All right, so why we're using SIMS? If you look at this scheme where these figures, you can see dynamic SIMS falls in this range and time-of-flight SIMS falls in that range. And this scale, it shows the detection range, and this is the analytical spots. As you can see, the dynamic range, this is the only technique that you can detect a very, very low concentration and give you a pretty decent analysis spot. So if you are looking at like very low concentration or very low doping elements, dynamic SIMS is one of the best analytical tool that you can use. And time-of-flight SIMS also gives you a pretty good analytical spot size and gives you a relatively good detection limit compared to other instrumentations. All right, so next I would like to talk about how the secondary ions has been generated. If you look at this animation, the red particle is the primary ions. As you can see, as the primary ions impinge the sample, it actually implant into the materials, but the energy kind most of the energy kind of like have a collision with the ions, with the atoms inside the materials. And part of the energy has bounced back to the surface and forms this thing called collision cascade. And only the first or second layer of the materials can be ejected out. So that's what we call escaping depth, also the information depth. And that is why the secondary ion mass spectrometry, the information depth is only the first 1 or 2 monolayers, because only that portion of the atoms can be escaped from the surface. And this, the secondary ions escape from the surface normally carries pretty small kinetic energy, is only in the a few electronvolts range. And as you can see from this pictures, the secondary ion species ejected can be positive ion, can be negative ion, and can be neutrons. And it also can be electrons. When the secondary ion is coming out, it can emit as a single atoms, a single elements. It can also eject as a cluster ions, which we call fragments. Depending on the stability of the molecule, it can eject as a whole organic molecule. It can, if it is not that stable, normally it will be chopped off to very small fragments and to eject as a smaller master ions, master charge ions. All right, so let's talk about some of the definition of SIMS, dynamic SIMS versus static SIMS, because a lot of times it is kind of confusing. When people talk about TOF SIMS, they often think about, because TOF SIMS is initially designed as a static SIMS, and then gradually they put a dynamic a sputter down so that we can also use as a dynamic SIMS. But in tradition, the dynamic SIMS is in another design using other type of configurations, which means the primary ions current is very high in nano M range. So when you sputter the materials, it will remove the material, gradually remove the materials, and you, during this process, you destroy the chemical bonds. So only elemental analysis can be done using traditional dynamic SIMS setup. The ion source we're using before is normally just oxygen, cesium, those atomic ion source. And you got a minimum molecular information. So this optical image shown here, you can see this is before the sputtering, and that is after sputtering. You can see a crater has been generated very easily. So in static SIMS, in the other hand, the primary ion beam current is very, very, very low compared to dynamic SIMS. In this mode is in the pico-M range. So it's about at least 1,000 or more than 1,000 smaller ion current, ion flux. So in this mode, you can do molecular analysis. You can look at the surface contaminations, like the surface compositions. So when you are doing static SIMS, those primary ion dose, basically you maintain very, very low, so that ionization event has very high probability of origin from a pristine and disturbed surface. That means the primary ion beam hit on the same spot during the analysis is very, very low. That's why you can make sure the secondary ions coming from the surface is from a pristine and disturbed surface. So that is shows the molecular information. So assuming the It is true silicon has a 10-15 atoms per centimeter squares. During static SIMS, that means less than 1% of the surface is disturbed. That means like less than 10 to 13 atoms per centimeter squares has been touched by the primary ion beam. So it's kind of low. So if you look at the directly dynamic SIMS and static SIMS, the most significant difference is in dynamic SIMS, it analyzed surface has been thoroughly damaged, eliminating most bonding information. For example, if you're looking at polymers, you will not see the molecular species of the polymer. You end up with just carbon, hydrogen, nitrogen, some other elemental information from the polymer. But for static SIMS, the primary ion flux is kept really, really low to ensure the ionization events occur from pristine surface. And so the goal of the static SIMS is to generate molecular information that representative the sample surface. Or sometimes if you are using GCIB, which is gas cluster ion source, you can do a molecular depth profile. That's a whole different story, and using another type of bulky ion source to maintain the molecular information. And unfortunately, in our instruments, we don't have this source. All right, so let's just do a simple math to just reiterate the static SIMS and dynamic SIMS range. So normally the static SIMS limit is 10 to 12 ions per centimeter squares, which is 0.1% of the surface site. Imagine if you are using 1 nanoamp current and sputter within a 500 micron by 500 micron area, you end up with 2.5 times 10 to 12 ions per centimeter square per second, which means you are reaching the static limit less than 1 second. If you continue to make the primary ion beam, the current smaller, down to 0.3 picoamp, which is the condition we're using normally, you can see like it will take 1,300 seconds to reach the static SIMS limit. Well, normally using dynamic SIMS, we have 20 to 200 nanoamp current. When you're sputtering to smaller area like 200 by 200, 1 second you can remove at least 2.3 layer of the materials. That means like maybe 1 or 2 nanometers. Okay, so this is just like a scanning tunneling microscopy STM image before and after static SIMS conditions on silicon surface. As you can see, before analysis, the silicon surface looks very, very clean, very, very nice. And after exposed to 3 times 10 to 12 ions per centimeter squares, some of the spots has been destroyed, but most of the area still looks pretty good, and still a lot of area has not been touched. All right, so here shows a few dynamic SIMS instruments. This is Atomica 4300 quadrupole. The quadrupole means the mass analyzer. And this is the chemical magnetic sector. So this instrument, the mass analyzer is using the magnetic sector as the mass analyzer. There are several universities around United States has this type of instrument. So this instrument gives you a really, really good detection limit. You can look at things in pp part per million, or for some elements you can even do part per trillion. All right, so over here, this is the instrument we have at AIF. Is time-of-flight secondary mass spectrometry from Einthof, Germany. And this is TOF SIMS 5. Right now they already have M6 Plus, like a really advanced model. But this instrument still can serve a lot of our current needs. Over here, you can see this is the bismuth source that provides the primary ions. And this long tube is time-of-flight mass analyzer. So basically, the secondary ions will fly in this tube and reach the detector. And over here, we have a cesium source and C60 source. The C60 source has not been used for a while. The cesium source has been used constantly. So that offers the dynamic SIMS capability. Over here is the stage we normally use. As you can see, we can accommodate a lot of samples at one time. And the size of the sample, this is 12 by 12. The hole over here is about 12 by 12 millimeter range. So since this is a back mount sample holder, which means you're putting the sample from the back of the sample stage, your sample needs to be a little bit longer, at least in one side, so that you can put it in without drop through the hole. If your sample is too small, we can actually put it in this circulate position. If it is too large, then we can put in this big hole over here. Since the distance between the sample holder to the extraction hole is pretty high, in some cases, if the sample is really thick, you can even put it on top of the stage, and we can still accommodate that too. So the sample size is not really critical. It could be smaller or it could be larger. But if you want to put multiple samples, at least like 10, then it's better to be in that range of size. All right, so let's look at how TOF SIMS really works. Over here, this is the sample. You put the sample in the stage. That's the primary ion beam source. This primary ions has been pulsed in a very short pulsing ion package. It shoot on the sample, interact with the sample, and then you generate a lot of secondary ions from the surface of the materials. And as you can see, those secondary ions are a different size. That means they carry different mass. And they separate by their flight time. So the lighter the ions, the faster they will travel to reach the detector. And then eventually you can see a spectrum that shows the different mass per ions charge ratios. And this process is actually really fast. For one pixels, or one data point, it takes about 100 microseconds. You can look at mass charge ratio at 800. And this process is keep going and going until you get a pretty good signal to noise ratio. So it's accumulation process, actually. The way it calculates the time or calculate the mass, or you use time to correlate it to mass, is just very simple equation over here. The energy equals mv squared divided by 2. The energy is the one that applied in the extraction over here. It's normally 2000 electron volts. And it is basically the same for every single particles. So if you rearrange this equation, the m over z equals to 2e divided by L squares and T squares. So the L is the distance between the sample surface to the detector, and it's supposed to be the same for every single element. So the m over z is actually proportional to the time. So the smaller the ions, the lighter the ions, the smaller the time it used to reach the detector. It's very simple design and very simple theory over here. Yeah. All right. So using time-of-flight SIMS, we can first get a mass spectrum that gives you the detailed information about the molecular structure from the surface. In the same time, since we are raster the beam over a selected range, you can get a mass spectral imaging and then shows the different species, the spatial distribution. With the cesium ion beam use alternative mode, you can actually get a pretty decent profile elements as a function of that. So later on, I will give you a lot of examples to show how this can be done and what the capability they have using this instrument. Just give you a very brief idea on how the spectra looks like. Over here, this is surface spectrum of polyester, which is a very common polymers using in plastic, using in fabrics. And this is the chemical structure of polyester. In a positive ion spectrum of PET, as you can see, you can have 104, 148, 149, 193. So these are all just fragments from this single polymer repeat unit. And the intensity of these ions depends on their stability. The 104 over here is probably the most stable ions among other fragments. In a negative ion, it shows totally different ion fragmentation patterns because it is negative ions. In 76, that's just like simple benzene ring, and 120 and 121 is the one with one CO2, and 165 is this fragments. So whenever you see a spectrum shows these several fragments together and the intensity ratio is similar, then you can determine this polymer at least contains a polyester fragment, polyester repeat unit. So using TOF SIMS, you can actually identify CMS, polyfragmentation ions.
Elaine, you locked up. You may want to repeat what you just said. You locked up for a little bit there.
Oh, okay. I just saw that my internet is not stable. Okay. All right. So what I said just now is we can using TOF SIMS to identify many different polymers because each polymer has their unique ionization patterns. And we also had a library of polymer, many polymer spectrum, so that you can use to kind of like doing cross-reference match. All right, so besides the spectrum, we can also do a surface imaging. How it works. All right, so this focused ion beam can be rastered in a selected area. You can divide this area to many pixels, like scanning electron microscopy. And at each pixel, you generate a spectrum. After a certain period of time, you can get a total area spectrum from this region. After you get the spectrum, you can select the ions that you are interested. For example, this is total ion image of pig skin cross sections that have been applied with a sunscreen lotion and shine with UV light. So this sunscreen lotion has titanium zinc oxide nanoparticles. what they want to do is to see how the titanium particles penetrate through the peak skins. So over here, that's the top layer of the peak skin. So that's it. If you're choosing CH3 ions, you can see this is the distribution of this peak skin. If you choose titanium, the titanium ions only appears on top of the peak skin. So you can easily tell the spatial distribution of different chemical species with very good spatial resolution. Normally in the imaging mode, we can control the spatial resolution down to 300 nanometer scale, which means 1 pixel is 300 nanometer. And you can also select a region of interest to reconstruct a spectrum. And that sometimes is really helpful to compare the chemical difference between different areas. All right, since we are talking about mass spectrometry, I would like to take a few seconds to talk about the mass resolutions. So over here, the mass resolution delta M is measured as a full width of half maximum of intensity of a spectral peak above the local background. In TOF SIMS, we are using the, so over here, that's the 10% value. In TOF SIMS, we are using the 50% value to define the mass resolution. So the resolution or delta M, as you can see, the smallest mass difference for which the two peak M and delta M can be resolved. That's the two different peaks can be resolved. Just give you an idea of how nice or high mass resolution work, looks and low mass resolution works. This is the one we get from our high mass resolution setting. As you can see, as for mass chart ratio at 26, we can easily separate the CN minus peak, which is the first one, and C carbon and carbon 13H2, or H, sorry, this is H peak. But using the low mass resolution setting, those peaks are kind of merged together, so you cannot separate them. This is so-called unit mass resolution. So in TOF SIMS spectrum, we often use resolving power instead of mass resolution to define our mass separation capability. So the resolving power is defined as M divided by delta M. And this resolving power is actually different if the mass is different. Okay, over here, over here is this delta M is 0.5 M over Z. That's how we defined our mass resolving power in TOF SIMS is 50% of the value. So that gives you the resolving power 2000. But if you are using 10% of value over here, that delta M is kind of 1 mass to chart ratio. And that only gives you 1000 resolving power. So in that sense, if you are using 50% value to define the resolving power, you normally get higher resolving power value. Okay, so this is the peak at mass to chart ratio 27. As you can see, you have 1, 2, 3, 4, 5 different ions, and the resolving power around this is about 7,000. If you're looking at mass to chart ratio at 199, the resolving power looks really, really high because the resolving power is M divided by delta M. So the higher the M, the higher the resolving power. This is a little bit confusing for a lot of people when you first see this. So in the typical SIMS spectrum, because a lot of surface has many adventurous hydrocarbons, so you will see a lot of carbon, hydrocarbon fragments. In the positive ions, most likely you will see hydrogen. And that's very common. So the first peak appeared in your spectra is hydrogen, and then you can see a set of one carbon cluster. And then followed by, sometimes you have sodium, and then 2 carbon, 3 carbon, 5 carbon. In a negative ion spectrum, you normally see really high hydrogen. Very interesting, hydrogen appears very high in negative ions. And then 1 carbon cluster, sometimes you have oxygen, OH, and then 2 carbon clusters. See, this is the one we take using our instrument. It illustrates is 1 carbon cluster, 2 carbon cluster, 3, 4, 5, and 6. You can sometimes see 7 or 8 if that is polypropylene or polyethylene polymers. And this spectrum can actually help us to do the mass calibration, because sometimes when you change the reflectron or some instrument setting, your spectral will off a lot. When you try to find the peak at 12, which is carbon, it is actually not there. It's 12.5 or sometimes it's 11.5. But if you can find those patterns and you can determine, okay, so this is carbon, CH, CH2, CH5. If you remember the pattern of carbon or carbon 2, then you can easily find, you can easily calibrate the spectrum. Okay, so when we look at the surface imaging, sometimes it's very confusing to a lot of people because they like to use the intensity of different species to quantify the amount of materials over there. However, in TOF SIMS, you cannot do that because the secondary ion yield from different species are very different. But you can directly compare the intensity within an image. For example, this sodium, this area is really bright. That means you have more sodium in this region compared to this really dark region. That basically shows no sodium. If you look at sodium ion versus this ions, which is one of the lignin from the wood cross-section, this the maximum count per pixel over here is only 26, and this maximum count per pixel is more than 3,000. But it doesn't mean you have more sodium than these ions in these materials. Simply just because sodium is really easy to ionize, it's really easy to detect it. It doesn't mean that it has more concentration. So in a simple word, the intensity of the ion is not proportional to the concentration. So don't ever use the ion intensity of the materials to determine how much is there. Okay, so the secondary ion yield over here is depending on many features. The primary ion current is basically same for all species. The spectral yield is different. The ionization probability is also different. And the concentration of the species is also different. The instrumental response factor is basically quite similar to all the species. So that's why you cannot use the ion intensity to determine the concentration over here. Okay, so this is the periodic table. What this figure tells you is the ionization probability and electronegativity. So the one on the left side tends to form positive ions. The one on the right side tends to form negative ions. So a lot of people came to me and say, how do you know what polarity we're gonna detect, what polarity you're gonna use? And so my simple answer is, a lot of times you really don't know. So you need to take both positive ion and negative ions and see which spectrum gives you a more information. And sometimes they can show both, they can show very valuable information from both positive and negative. So just simply do both. You cannot take positive ion spectrum and a negative ion spectrum at the same time, but you can do it at different times. All right, so I will very briefly talk about the TOF SIMS instrument and then leave some time for the applications. It runs really fast. All right, so in our instrument, we have ultra high vacuum, which gives you 10⁻⁹ and bar in the analysis beam. And you got a primary ion gums to give you a short, less than 1 nanometer ion pulse, give you a smaller beam size for high spectral resolution imaging. And you got an electric flood gun for charge compensation. So you can do a insulating sample easily just using flood gun to neutralize the sample, the charge accumulated on the surface. And then you have a time-of-flight mass analyzer to give you high mass resolution, high transmission. And most importantly, give you parallel detection of all masses, so you didn't lose any mass during the analysis. All right, so this is a little bit complicated to show how the liquid metal ion gum, how the lenses and all the column over here. But basically, if you look at here, that's the bismuth beam source part, generate the big ion beam. And this part is focusing, so focus the beam in a smaller spot size. And this is the pulsing unit. Basically, you cut the DC beam to a pulsed ion beam to a very short pulse ion beam. And then this is the final focusing part that gives you to shape your beam, the size of the beam, and then finally focus on the samples. All right. And that's the mass. So the last part I would like to talk about is the time-of-flight mass analyzer. So that's the sample, and on top of the sample, you have an extractor. So the distance between the sample and extractor is maintained at 1.5 millimeter. If it is higher or lower, the secondary ions will not go through the extractor, will fly to either this side or that side to hit kind of outside the vacuum. Just go to the vacuum. It will not go to the time-of-flight mass analyzer. And we got a reflection over here that basically used as a energy correction, because for the same mass to charge ratio, when you bombard from the materials, they might carry a little bit difference about the kinetic energy. Some of the ion has a little bit higher, some of the ion has a bit lower. So the ions, so this M plus and that M plus has the same mass to charge. Yeah, they are basically, it's the same ions. For example, we can say this is hydrogen, both hydrogen. So the hydrogen has a little bit higher energy, it will go faster, faster, faster. And when they go to the reflectron, this is a series of electron fields. And it will go a little bit deeper into the reflectron field and then reflect it. And this, the one with the lower energy, contrast, it will go kind of like a little bit shorter range and then go back to here. So that means even though they have different energies, they didn't fly the same length. The one with high energy flied a little bit longer, and the one with lower energy flied a little bit shorter. So eventually that cancels the difference between the energy over here, and they will go to the detector at the same time. And that gives you a very, very sharp mass resolution. If you don't have the reflectron over here, you will see a much more spread of the peak. So the mass peak will be broader. That will give you a little bit difficulty assigning the peak, the ions. What are they? What is the chemical compositions? All right, now let's talk about some of the applications over here. So I will try to cover a few from different applications or different aspects, showing some spectrum and interesting images, imagings, and a few depth profile examples. Okay, so this is actually the first project I worked on when I came to analytical instrumentation facility, and it's something about the dyed the dyed materials on polyester. So I look at the different dye molecule and the different dyed fabrics. This is a simple dispersed blue dye 60. As you can see, it has a chlorophore. And the mass shot ratio is 423. If you look at the positive ion spectrum, it shows a lot of distinctive fragmentations. And all those can be visualized by cutting here, 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 here. And you got so many different fragmentations. In the negative ion, it's much more simpler. You got molecular ions, you got the one that cuts 1063, you also got 306. That's also pretty stable. So this is the absolute counts for positive and negative. It is pretty easy to understand in the negative ions, these ions are more stable so that it shows much more counts, but they all coming from this one materials. So these are all coming from one organic molecules, but they just simply shows different ion intensity because of this stability. Okay, so this is also a fiber. Since we are so close to our college textile, we receive many samples from them. A lot of the applications I show here are related to fibers, fabrics, things like that. So this is actually a single fiber, which is a nylon. And so this nylon fiber has been coated with atomic layer deposition with titanium oxide. And on top of titanium oxide, they deposit a silver using a I think they put it in a silver nitride solution, and they do some simple chemical reactions, and they try to deposit the silver on top of the titanium oxide. Since this is a very thin layer, the atomic layer deposition with titanium oxide is very thin. The silver deposition is also very thin. If you're using SEM or EDS analysis, you probably even couldn't detect those because the layer is too thin and the interaction volume of SEM is much more thicker. However, if you're using TOF SIMS, you are looking at very top layer of the surface, and you can easily tell what are on top of the surface. So that means TOF SIMS is very good technique to look at the surface modification, thin layer surface modification, because you can easily tell the surface chemistry change after each step. Over here, as you can see, the silver is kind of form a spiral type of kind of like line along the titanium oxide. And that over here shows titanium. That's the overlay of this two. And very clear distribution of titanium and silver over here. And no need coating. Another fiber, fiber examples. This is a fabric, a nylon fabric, dyed with this type of acid blue 25, with this molecular information and mass spectrometry 393. And this fabric was simply embedded in a resin. And after cure, they use cryomicrotome to cut in small pieces and lay flat on the silicon surface. And so over here, that's the round particle over here. That's simply just a fiber cross section, and that over here, that's the resin substitute. And SO3 and this molecular ion clearly shows the chemical information inside this fiber. Very straightforward method to look at the chemical spatial resolution. All right, so this is a really interesting examples. I'm not sure if you heard about this story or not, but I would like to talk about a little bit more. Since TOF SIMS is very surface sensitive and it only analyzes the top layer of the materials, we can use this to kind of look at the thickness of ink and pencil thickness. And we call this is a forensic, campus forensic analysis. We got the sample from an engineer, from a professor from an engineer, because he suspected one of the students was cheating on the final grade, because the student asked more scores, and the professor suspect the students use the wrong answer, and then write the right answer, correct answer on top of the ink mark. However, after a few days, you really couldn't tell which one is written first, which one is written on top, since the ink really easy to kind of absorb into the paper and always looks written first and pencil on top. See, this is the optical image in this too. You really couldn't tell. Like for me, I would say pencil on top, ink first. However, if you use TOF SIMS, you can find the ions that are characteristic to ink, to the ink chemicals. So for this one, is pencil first, ink on top. And over here, that's the whole stripe. That's the ink characteristic ion. If ink first, pencil on top, and that's what you see. So only this area exposed, not covered by pencil, can be clearly seen. And over here is very red light. So you can easily tell which one is written first and which one is not. And eventually we cut a few pieces from the final grade and the paper, and we put it in the instrument and we test it. So all the results shows that pencil first, ink on top. So that means the students is not cheating. It's probably the TA is not trained well. Or maybe like he or she is very sleepy that day and didn't grade really well. And the professor is really happy that he didn't just say it without any proof. But it really cost a lot of time for us to figure out this. Of course, we didn't charge him, it just for fun at that time to kind of like test the capabilities. That is our one of the show and tell stories to visitors and tours to students. So the students know that they cannot cheat over here. We have some tools to, you know, to test it. All right, so for the depth profile, you use two beam to do the alternative. And so you use cesium to sputter, and then you use prism to analyze the bottom of the crater. And these two beam do the alternative way, you can eventually get a depth profile. This is just very simple example of momentum silicon thin film on top of silicon. As you can see silicon silicon ions in this film and also in silicon substrate. But of course, because of the chemical composition of silicon, over here you get a much higher silicon intensity. Right under interface, you can see fluorine contaminations. So it's very sensitive to look at the interface, to look at the contaminations. All right, it is possible to do the quantifications using ion-implanted standards. However, this only applies to less than maybe 5%, below 5% of the doping, because if it is higher than 5%, you will alter the substrate or matrix, and then the ion yield might be different. However, using the ion implant standards, you can do all elements and isotopes. You can look at the depth with the implant energies, and then the peak concentration can be varied with those. Over here in anti-state, we have over 3,000 implanted standards. Thanks to Fred. This is simple a depth profile of magnesium in gallium nitride. As you can see, we can look at 0.2 ppm. That is a very low concentration. And this is obtained with the Chemica MS6N. This is obtained using our own instrument. That's just simply a fluorine implant into a silicon. That's about, you can see the fluorine implant dose is 5E15 atoms per centimeter square. And when you convert the secondary ions intensity into a concentration, you can get this is about 2%. No, 5E15, 5E20. That's 2%, right? Right. All right. Okay, so that's another example. Also, in a thin film with silicon. Silicon is not actually a silicon doping. So the way they do this is they made this hafnium oxide film using atomic layer deposition method. So what they do is they 26 layers of hafnium oxide and then 1 layer of silicon, and then they do this. They keep doing this until they got 11 nanometer of hafnium oxide layers. So in this configuration is about 2.6 nanometer hafnium oxide in between the doping layer. So this silicon layer is actually very thin. It's probably even less than a monolayer thickness. They tried using TM cross-section and then EDS to detect silicon, but it's nothing there because it's below the EDS detection limit. So that's why they kind of sort SIMS to look at the distribution, how they behave. So over here, you can see this silicon depth profile. You can tell like there's 1, 2, 3, 4 layers. Of course, when you spread it down to the bottom of the layer, the depth resolution becomes poorer and poorer because of the ion mixing and also roughness generated by ion scattering. But you can still actually see the different layers. And with implantation of silicon into hafnium oxide, we can convert this intensity into a concentration. And that's what we got is about 1E21 atoms per centimeter squares. And that corresponding to 2% of our upcoming concentration. Because 5E22 is one model layer, that means 100%, and 1E21 is about 2%. With the combination of spectrum imaging and depth profile, we can also do very interesting three-dimensional reconstructions. For example, over here, the first layer over here is iridium, and underneath a tellurium nitride layer, and followed by a hafnium oxide, and then tellurium nitride layer. If you have enough spatial resolution, you can actually see there's iridium, there's 2 tellurium nitride, and that dominated by the hafnium oxide. And you can overlay these three to display as a very, very colorful and beautiful three-dimensional reconstruction. Okay, so the last topic I'd like to touch on is the backside SIMS analysis. And this is the method that developed by Fred, Stevie, and Roberto at our lab. And that it has been extensively used by a lot of semiconductor industries to get wide applications. So the reason we do this is because sometimes we want to look at the diffusion of top layer to the bottom layer. If we started from the top, we actually have a lot of ion mixing and roughness, things like that. In that case, you really couldn't tell this is real diffusion or it's because of ion mixing. For example, over here, we want to look at whether copper diffuse in tellurium nitride layer, and even for the silicon oxide layer. If we sputter from the top, we can see this goes to really, really high, and then it goes to the silicon oxide layers. And it looks like a huge amount of diffusion into the silicon layer. However, if we do a backside polish, which means you polish from the back, you polish most of the silicon substrate, you remove the silicon, and leave about 200 nanometer silicon on top. And then the ion beam comes through here, you sputter from the silicon surface, which is the backside. And then you reach the layer of interest first, which you don't have any disturbing from the top layer. And then we can see you actually got a totally different results. So that's from front side analysis. And this is from backside analysis. You see there's nothing, no gold at all in the silicon oxide layer. No gold, no copper, not gold, copper at all in the tellurium nitride and tellurium layer. And it's really sharp leading edge for copper. So very clean copper distribution. As you can see, the difference is dramatic, and that actually tells a lot of stories, answers a lot of questions, that definitively. And this is the profile that obtained using our TOF SIMS instrument. Similar configuration is 10 nitride copper from backside. All right, so I think I already talked almost an hour, and that's basically end of this talk. And the take-home message is, so after this, I hope you get, SIMS is probably the most sensitive analytical technique for hard materials. And you can know what is the difference between dynamic SIMS and static SIMS. And our TOF SIMS instrument can perform both dynamic SIMS and static SIMS if they are being right. And for the high resolution mapping, we get 300 nanometer spatial resolution. And for the depth resolution, we can do 2 to 3 nanometers using a low energy spectrum beam. So with that, I will end my portion, and you can ask questions. So I think I should unmute all. How can I do unmute all? I see.
Elaine, you may want to ask if any of the people that are on now have any applications they wanted to discuss, and if they wanted to get a copy of the slides, that you could make a PDF available.
Okay. Yeah, sure. I can send you the PDF for you if you're interested. And I think this is also recorded in the cloud, and I can share the link with you later on. And if you have any questions, don't hesitate to drop me an email. Should I write my email here? Oops.
Would it be possible to ask a question right now?
Yeah, please.
This is Tim Spiel, University of Illinois. I've got a Trift 3 from physical electronics. So different type of spectrometer, but same idea. My cesium gun, we originally set it up for depth profiling at about 2 to 3 kilovolts, although the gun can run up to about 15 kilovolts. It seems to me that you get a trade-off. At higher energies, you have a nice flat bottom crater, but for low energies, you have less intermixing. You looked at anything different with different energies of your cesium gun during depth profiling?
Yes, we have 3 different settings, 1 keV, 3 keV, and 10 keV. So what I can see is, like, with a higher energy, you got a sharper, you got a better beam spot size or resolution for X and Y. So you got a sharp crater edge, or probably gives you a flatter bottom or roughness. But with higher energy, you also sputter much faster. But you got a poor depth resolution compared to the lower energy. I didn't. I think, like, are you doing the same materials using different energy, and you got a different roughness?
Well, actually, we've only really been using the low kV, but I was wondering what might be other advantages for the high kV.
High kV. High kV gives you much faster sputtering rate. If you're looking at films at like more than 1 micron, you probably want to use higher energy sputtering setting.
You might also mention if you're sputtering faster, you probably get a better detection limit. And I'm not sure if he's aware of the paper we did with Andrew, showing how to improve the detection limits on the TOF.
Actually, I'm not. Could I get that reference?
Yeah.
Sure, $29.95. Send Elaine, do you want to put up your email address?
Yes.
So send your email address.
Yeah, that's my email. Very simple. Yeah, I think the most difference for me with the different energy is lower sputtering energy gives a much better depth resolution, but much slower sputtering rate.
Yeah, there was a professor here at the U of I, Ed Seebauer, who was using the low energy to get very, very surface sensitive depth profiles.
Very surface sensitive means like within 5 nanometer.
Yeah, very, very close to the surface.
Yeah, that's true. See, over here, the HFO2 film, this is only like 11 nanometer. So you have to use 1 nanoamp. No, not that. You have to use 1 kV energy. If you have 300 electron volts energy, that will be even better to give you a good depth resolution. I tried 3 kV energy on the same configuration, the same materials. You even couldn't see the silicon layers. So that just that much difference.
Yeah, unfortunately, my my almost 20-year-old cesium gun, I'm kind of limited to about 3 kV. You'd be able to do 2, but now I can't keep a stable beam below 3.
I see. Yeah, that's true. It's hard to maintain the stability using low energy. The current is pretty low too.
But what I haven't been doing recently is trying the higher energy, which is what I think I'm going to try to do when I can get back into the lab.
Yeah. Okay. So any more questions and suggestions?
Elaine, this is Dan Sand with Loperex. So your talk included films and fibers. Is there any limitation to the geometry of the sample that you can run, the topography?
Of course, the flatter the better, because the flatter sample gives you the better mass resolution. If you want to identify the chemical configurations or chemical compositions, of course, the best mass resolution gives you a more accurate peak, more precise peak assignment. Like for the fibers, you see the fabric is actually not flat, and we normally kind of use the hydraulic press to make it flatter to give you much better mass resolution. So we do not like the raw kit type of materials.
Thank you.
Mhm.
Let me throw out another interesting question here.
Mhm.
What has been done concerning static SIMS and standards? You mentioned use of standards for depth profiling.
Yeah.
Has anyone really delved into the question of surface scans and standards?
That's a really, really, really difficult question to I think, very different problem to solve. But one thing you can do is you can incorporate internal standard into your sample. Or the reason that people don't use time of flight as a do the quantification is the chemical fragmentation is so complicated, and it's also related to different matrix. So for the same materials into different matrix, it gives you a different second ion yield. It gives you a different second ion intensity. And then for one materials, you can get as many as possibility or as many as different ion fragments. So how you can do the quantification for every materials, that's very hard. XPS is possible because you are dealing with elements and there's only that many elements over there. So you can do the relative sensitivity factor of different elements versus carbon, which is same elements.
For certain matrices, there is another approach. And for example, for the silicon technology, we were successful in using ion implantation through a removable oxide layer. And the peak of the implant was placed at the interface between the oxide and the substrate. So when you etched off the oxide layer, you now had a known amount right at the surface. So if you've got a material where you can have something on the surface you can remove and figure out the ion implantation, then you can have something which is a known concentration at the surface. But it's a rather limited subset. You're not going to be able to do that very well, I think, with an organic.
Yeah, so for organic, it's going to be a really, really tough question. But you can do a relative comparison between different samples, different substrates.
That's generally what I suggest for my researchers as well, is to try to find something that's as close to a matrix material as possible and do ratios to them.
Yeah, that's true. Or you can incorporate internal standard.
The only downside to that would be if when you covered it with your molecule, you're hiding some of the surface. So the thing you're assuming to be constant isn't necessarily.
Yeah, that's true. So you kind of overestimate the result. Because your matrix ion is buried and the ratio will be much higher than it's supposed to be.
All right, thank you very much.
Yeah, thank you all
thank you
all for the attendance. It is well attended, I think, to me. I'm gonna save all the chat. Thank you all for the attendance. So if you have any questions, just please don't hesitate to email me. All right. So with that, I'm gonna end the meeting. All right. Right, only two of us now.
So, Elaine, I thought that went very well.
Okay.
I think you need to drink more. Your voice started to go at the very end.
Yeah, that's true. I can only talk maybe half hour for good. And then
That's why I drink a whole lot.
actually, my husband provided me a cup of water. I forgot.
Good. So there were 10 participants. I'll send you the screenshots so you have them. There were 4 from our group, you and me, Anton, and Phoebe. And the person from University of Illinois sounds interesting. And
You know him?
once again, he's not aware of any of our papers. So I would suggest you send him 2 papers. One of them is the improvement in detection limit. And the other one is the first mosquito paper.
Okay.
So he just has a couple more ideas. And from what Dan Sand wants to do, you know, his materials may be all kinds of stuff, but you mentioned use a press. And I think he understood that if you don't have an even surface, your mass resolution is going to suffer. So I think that's fine. Just thinking about things, because I have to do one tomorrow. The last slide should have your email address on it.